Hello students, welcome to Unit 8 Notes, Section 5.2. I have tried to make this video a couple of times and it has failed on my iPad, so I reset it, but that's why you see the warm-up done. So I guess I'll just leave it and go through it quickly. Please disregard all the spelling errors. I must have been making this warm-up quite quickly and while I was typing it out, made a couple errors. So all right, number one, at 8 p.m., the temperature began dropping at a rate of 1 degree Celsius per hour. 12 hours later, it began rising at the rate of 1.5 degrees Celsius per hour for 6 hours. What was the net change in temperature over the 18-hour period? So you see I did negative 1 degree Celsius times 12 to get negative 12 degrees Celsius. Then I did 1.5 degrees Celsius times 6. That's a positive 1.5, which is a positive 9. And I added those together to get my net rate of change, net change, which was negative 3 degrees Celsius. All right. Number two, if I go too fast, just pause the video, okay? Number two, water flows over a spillway at a steady rate of 300 cubic feet per second. How many cubic feet of water pass over the spillway in one day? So I took 300 feet per cubic per second and I multiplied it by, you can do minutes then hours, but there are 60 seconds in a minute, 60 minutes in an hour, so I just did it by 3,600 seconds in an hour. And then I multiplied it by 24 hours in one day. And I reduced hours divided by hours and seconds divided by seconds, which gave me feet cubed per day. So multiplying those all together, you get 25,920,000, almost 26 million cubic feet per day pour over this spillway. All right. Third one, a city has a population density of 350 people per square mile in an area of 50 square miles. So what is the population density, of that city? So I just did 350 people per square mile times 50 square miles, and that gave me 17,500 people. All right, the last one. A hummingbird in flight beats its wings at a rate of 70 times per second. How many times does it beat its wings in an hour if it is in flight 70% of the time? That's supposed to be time. Well, 70 times per second, there are 3,600 seconds in 1 hour. So I multiply them together and I get 252,000 times per hour, which is crazy, but hummingbirds, that's how they stay in flight. And I multiplied that by 0.7, or in this case, 7/10 or 70%. And that gave me 176,400 times because it was only flying for 70% of the time. Okay, so this warm-up is for Unit 8, Note Section 5.2 of our distance learning. Just like we did before, we're going to look at areas under the curve. So for number one, for instance, let me take number one and let me graph it out on a curve, okay? So let's say that I were to graph for 12 hours a consistent rate here of negative 1 degrees, okay, for what was it, 12 hours? Yeah, let me try that again. So for 12 hours, we have this area right here, right? So let this axis be degrees Celsius, and this axis can be time in hours. And so negative 1 times 12 is negative 12. And then what we have is at about 1.5, which is probably somewhere up here, we have this happening, which would be, whoops, that's your 6 hours. So this would be time would be 18 here, from 12 to 18. And this is at 1.5, positive 1.5 degrees Celsius per hour. So this is happening, whoops, that area is happening. So 1.5 times 6, again, is plus 9. And that, what we're going to do is we're going to add those areas together, and we get our negative 3. Negative 3 degrees Celsius. So in this case, we have a negative area and a positive area fighting each other. So for section 5.3 and 5.4 that we move on to, you'll actually be able to calculate this using a function. But for now, and we're going to be doing integral calculus. So we're going to be using integration. For this one, I want to introduce you to the notation, make you more confident with using the notation, really making it as easy as possible to work with the notation. Because calculus textbooks can be a little bit difficult in understanding what they're trying to say. Remember, the contributors to calculus are Isaac Newton and Leibniz. There are others like Riemann for Riemann sums. So we'll be looking at him today. George Riemann, I think his first name was. And and we'll relate that to our integration that we're doing. Okay, so today your main focus is knowing your geometry formulas because they're going to come in handy. So you're going to need to know the area of a triangle, the area of a square and rectangle, the area of a circle, and yes, the area of a trapezoid. So the area of a triangle is 1/2 base times height. The area of a square rectangle is just base times height. Area of a circle is pi r squared. And the area of a trapezoid is, there's a couple ways to write this. I like to call it the average of my legs times my height. But again, you could write it differently. You can say the average of the bases. Actually, I'm sorry, I like to call it by the bases because we have 2 of them, times height. Or I've even seen this formula that sometimes, especially when you're using Go formative, you might want to write out this formula 1/2 times b1 plus b2 times height, where you can put your 1/2 in parentheses itself. Okay, so if you're entering in a calculator, like a Go formative, you might want to do 1/2 like that to show your work. Okay, just make sure you're doing 1 divided by 2, and that's separate from adding your bases together times your height. Okay, so it's really any one of those formulas, but remember, you're going to average your 2 bases times the height. So you'll need all of these for the lesson today. So I will leave that at the top of your notes, your digital notes that I upload. All right. So let's talk about subintervals. Well, let's start with, here's what we'll be talking about today. Riemann sums, okay? Literally the word sum means to add. Terminology and notation of integration. So we're going to talk about the uniqueness of sigma versus elongated S. Okay, so they both mean kind of the same thing. This one is a Greek letter, sigma. It's, like I said, Greek sigma. It's a capital sigma. Okay, lowercase sigma looks like this. So capital Greek, here, let me just write it here. Capital Greek sigma versus, this is an elongated, I hope I don't spell this right, wrong. Elongated, elongated Roman S. Whoops. I will come back and correct that if I spell elongated incorrectly. Okay, the definite integral, which is going to be this right here, from a to b of a function with respect to a variable. And so we're going to see how it goes from being an elongated, a Greek sigma, capital Greek sigma, over to a definite integral. And then we're going to compute them. We can compute them on a calculator, but I'm not going to show you how to do this yet. I'll show you this in section 5.3. Let me change the color. Okay, and integrability, which is integration. Okay, so let's take a look at our first set of notes. So the definite integral. When we're looking at this, we have, remember, a width of a portion. We have a width of a rectangle, and that width we call delta x. And what we did in our last section in 5.1, we kept these all the same width. Okay, they don't have to be. Okay, the subintervals can change. And you see that it starts at one interval, we call it 1, and it ends at an interval n. All right, so each one of these rectangles is going to be added together, and they're partitioned. So let's take a look from A to B here. We might want to make the rectangles all wide, or we might want to make them a little bit skinnier. So as everyone was studying calculus in the time that they were making their discoveries, they realized collectively that if we were to make rectangles really, really skinny, the skinnier we make them, the more area that we fill in and the less of an issue, an over or underestimate that we have. It's a really great idea to be able to manipulate the size or width of them. And in theory, if we could make our rectangles have no thickness, imagine if delta x was approximately 0.00000001 wide. Wouldn't that be great? So what we're going to do is we're going to call this limiting delta x to 0. Okay, so that's the goal, is to really get delta x, the idea of how wide a rectangle is, really down to a width of nothing. Okay, so that brings me on to here. Well, here's just some information. Here's background information. So in the preceding section, we estimated distances, areas, and volumes with finite sums. The term of the sums are obtained by multiplying selected function values by the length of the interval. Okay, here we have the first view of sigma notation. So k being 1 is, again, your first rectangle per se, and then n being your last rectangle. Now they don't have to be rectangles, but in theory we're just going to be adding these items together. So this is your beginning, this is your end. Remember, these are the beginning and end of the things you're adding together, those intervals. So sigma notation enables us to express a large sum in compact form. So we're not going to write all this down, but we're just saying, like, this is what we're going to be using right here. So the Greek capital letter sigma stands for sum. The index k tells us where to begin the sum, and at the number below the sigma, and where to end the number above. If the symbol infinity appears above the sigma, it indicates that the terms go on indefinitely. Okay, so sometimes we're talking about a definite integral where it ends. That's great. If it's a number, then it ends. It's what we call a definite integral. And if that number is not a number, if it's an ideal like infinity, it's called an indefinite. So it goes on forever. Okay, so the sum in which we will be interested in are called Riemann sums after, George Riemann, 1826 to 1866. LRIM, MRIM, and RRIM in the previous sections are all examples of those sums. Not because they estimate area, but because they were constructed in a particular way by adding them together, okay? So we begin with an arbitrary continuous function defined in a closed interval AB. So here is the existence of a definite integral. So the limit here, P is a partition. The goal is that we limit our partition to be nothing, right? Have no thickness and no size. That's what I was saying earlier, delta x being approaching 0. Okay, and we have k equals 1, that's your first, n being your last, a function. And in this case, the function is with respect to that particular rate of change of the variable x. And that is what we call the integrable. What you can, the integral. Okay, this right here is integral. Okay, I'm looking, sorry, from A to B. Yeah. So the existence of the definite integral is when we actually have numbers for A and B. So let's go to our next one. You'll notice that that same notation will continue on, but delta x, again, is that width we're talking about, how wide A to B is, divided by the amount of subintervals. Okay, that's your rate of change here. This all breaks down to something that I want to show you, this right here. So we have the limit as n approaches infinity, k is 1 to k is n, of this function with respect to x. And that really breaks down into what we're going to use, which is this very simple form of an integral. It's much more simple than all the stuff happening here. So this is what we call our upper limit of integration. I think this is on the next slide, but I'm going to write it anyway. Here's our lower. And then here's our function. And then this is the variable at which we are integrating. And I'm going to show you what those all mean, okay? So let's go up a little bit here. It says the notation that Leibniz introduced for the definite integral was equally inspired. In his derivative notation, the Greek letter delta for difference switched to the Roman letters D for differential in the limit. So dy dx, you see here, was when the limit of the differential approached 0. Notice the difference. Delta x has again tended to 0, becoming a differential dx. The Greek letter sigma has become the elongated Roman s so that the integral can retain its identity as a sum. And the ck's have become so crowded together that the limit that we no longer think of a choppy selection of x values being between a and b, but rather a continuous, unbroken sampling of x values. So think about adding all those rectangles, rectangle, 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 rectangle. And instead of having that go on and on and on and on and on forever, you say, you know what, let's grab them all and let's make them a continuous function, which is really, really nice. So instead of going from one rectangle to the last rectangle of all these rectangles as everything is changing, we just say continuous function. Let's look at it between this number and this number. okay? So with all of that said, this is read as the integral from a to b. So you always start at your lower limit, go to your upper. The integral from a to b of f of x dx, or the integral from a to b of f of x with respect to x is how we're going to read this off, okay? Here is everything in one nice clean slide. So we have the lower limit of integration, your elongated Roman s called the integral sign, your upper limit of integration called b. Well, in this case, these are going to be numbers. You're going to put numbers in for these, okay? The function, so f of x is any function. It might be 5, it might be 3x minus 3. It's called the integrand. X is a variable of integration, so that's why it's a dx, not a dy. You can do dy, by the way. That would change this to be f of y, all right? And the integral from a to b, when you find the value of the integral, you have evaluated the integral, okay? Here, if you were doing f of t, it would be dt. If it was f of u, it would be du. And if it was f of x, it's dx. Again, it could be y as well. So no matter how we represent the integral, it is the same number defined as a limit of the Riemann sums. Since it does not matter what the letter we use to run from a to b, the variable of integration is called the dummy variable, okay? So if we have an xy coordinate plane, then a and b, let me go to this one right here. If we have an xy coordinate plane, and we have, for instance, a is 3. Let's do an example. Let's do 3 to 7 of 6 dx. You're like, okay, well, what does that mean? Well, it means f of x equals 6. So what does that look like? Well, here, I'll color code this orange. So what that means is you're really going to write that as a function. Whatever that number or variable is in there, you'll write as a function. Okay, so let's do f of 6. So here's f of 6. Okay, I'm going to graph it. Y equals 6. Or you could say f of x equals 6. That's your function. Okay. And now we're going to go between 3 and 7. So what we're saying is that x equals 3 and x equals 7. So what I'm going to do is put parameters on this at 3 and at 7. Okay, so I'll just, I'll make it a solid line. And this is just kind of like an idea, so it's not really lines, but I'll talk more about that later. And so here's what we're trying to find. We're trying to find how much area is there. Well, using geometry, you're going to say, Mr. A, that is between 3 and 7, and between 0 and 6. So it is a rectangle that is 6 units high by 4 units wide. So you just did your first integral. 6 times 4 is 24. So the integral from 3 to 7 of 6 dx equals 24. And we're done. You just did your first integral. It might look much easier the way I did it than what you saw above, but really we're just kind of cutting through all of that rigorous writing about what it is to be an integral and we're trying to make it simple so that you can just calculate them using geometry at this point. Now, you can't have variables in there. So for instance, we'll do a few of them, okay? So we'll do a few of them with variables in it, and that's fine. You just have to know that there's a beginning and an end point for these, okay? Now, the way I learned this in calculus was you your x and y, your upper limit and your lower limit. Let's start from the upper. So you always think about it from up. Well, you always go from lower to upper, but think about this 7 to 3. So watch this. Watch as I drag my laser pointer here. The first function, as I come from the highest x down to the lowest x, or the greatest from the lesser, I pierce the function 7 first, x equals 7, and I pierce the function x equals 3. Okay? We're going to do the same thing this way for your highest to your lowest. So really, what we're doing first is piercing 6, and then we're piercing 0. Now, how do we know it's 0? Well, you don't have to go from 6 to 0, but then what you have to do is go from 7 to 1, right? Because you would first, you have to have a difference of 6 because that's what the function is. So the same width will happen from 7 to 1. Think about if I move all of these up by 1 unit, move that up 1 unit. Well, now this needs to move up 1 unit. The bottom part would have to move up 1 unit if the top will go up 1 unit. Okay, so you're always going to have an area of 24 as long as y equals 6 is your equation. So what I'm trying to say is here, you have x equals 3 and you have x equals 7. Here you have y equals 6 and you also have y equals 0 because there's nothing else left in here. So you can think about it as two x equals functions and two y equals functions. All right. Okay, yeah, I'll explain it more when we get different examples, okay? So here's the first one. Oh, by the way, that's what we call area under a curve. So when we're finding the definite integral, we are finding area under a curve. So our units, I like to use units squared as my unit of measure. So I always end my answers with units squared, okay? So in this one, we have, look at this, we have x equals -2, we have that line. We have x equals 2, we have that line. We have y equals the square root of 4 minus x squared. We also have y equals 0. We know that because there's nothing else, there's nothing else connected to the 4 minus x squared, so we can just assume the other equation here that we're finding the difference between is 0, because that won't affect 4 minus x squared in any way, okay? So we have x equals -2, so think about that line. So here's x equals -2. And we have x equals 2. So you're saying, Mr. A, there's a lot that's not shaded here. I know. But once we put in all 4 of our items, you're going to see that it is, okay? We also have, we have y equals. So I'm going to start with y equals 0. Okay, so we have y equals 0. Here's this one. That line's a little bit too long. I'm sorry. Give me a second. There we go. We have y equals 0. Okay. And then the last line we have is really this curved line, this circle, and it's going to be y equals the square root of 4 minus x squared. So it's between all 4 of these. So now I have to ask you, by the way, that's a circle. the equation of a circle is x squared plus y squared equals r squared. So in this case, it would have been x squared plus y squared equals 4 squared. If you know the equation of a circle, sorry to bore you, but in this case, oh, I'm sorry, the radius is 2, right? Do you see how this radius is 2 units right here? 2 units. So 2 squared. So we have x squared plus y squared equals 4. Move x to the other side. Whoops. Move x squared to the other side. So you get 4 minus x squared. And then find the square root and then now find the square root of both sides, and you get 4 minus x squared into the radical. So I just want to show you it's the same thing, except in this case it's only in the positive quadrant, not in the negative, okay, because they wanted it limited to be only positive because that's the way they wrote it. Okay, so the textbook only focused in on the positive value for this one, okay? All right, so that was just a little recap. Sorry to get off topic here, but bringing it back. So that's where that equation came in and why that line is curved, because it's really the equation for a circle. Okay, so let me try to rewrite this one. Whoops. So that, okay, not too bad. So the question is, if I were to pick any of the area that's between all 4 items, where is that area? And you should clearly see that it's going to be this area right here. If I were to pick this area here, it's between the 2 oranges, it's also above the blue, but it's not also below the other blue, okay? So I'm bounded by this area, so it's actually going to be this right here is what I'm focusing in on, this area right here. Let me use this color. There we go. Okay. So the question is, where does everything fall in between? And this is where all 4 items, it satisfies both being greater than x equals -2, being lesser than x equals 2, being greater than y equals 0, but also lesser than y equals 4 minus x squared. Okay? And that's what I'm bounded by. So in this case, the area of a circle is pi r squared. So the area of our circle is equal to pi times 2 squared. So the area of our circle is is 4 pi. 4 pi. And we don't have a circle, we actually have a semicircle, right? So the equation, here's your radius of 2, right? R equals 2. So what we're going to do is area of semicircle is going to be half of that, which is 2 pi units squared. Okay, so guess what? The integral from -2 to 2 of the square root of 4 minus x squared dx is actually equivalent to 2 pi units squared. And instead of answering as area, we're actually going to answer as the integral. Nice work, everyone. Good job. This is one of your first integrals that you've done. I mean, you did another one above, but, and I know you're kind of following along, but give yourself credit where credit is due, okay? And that was your first integral. Now, let's do another one. Okay. We do have to be careful sometimes if the area, for instance, falls underneath the radical, underneath the x-axis, it's considered to be negative. If it's above the x-axis, it's considered to be positive. Do not worry for this section. Every question I give you will be positive. I'm not trying to assess you. I'm not trying to trick you. Okay, I am just trying to get you to do the area formulas that we talked about using geometry and relating it to the integral. But this was in this section of the textbook, so I threw it out there to you. Just know that sometimes the area could be negative. All right, it just depends on what we're evaluating. Again, this section we're not doing negative area. Negative area if below x-axis. Okay. Don't forget that the total area, so this is what I call total area, or sorry, net area. I apologize. Net area. Net area is when you do the area above the x-axis and you take away the area below the x-axis, versus total, which is when you do the absolute value of area and you add it to the other absolute value of area. So let's say you have 6 minus 2. Well, that's 4. So that means that you had 6 units above the x-axis, 2 below that, so you get a net area of 4. Where if you want total area, if I use the word total, then you want to do 6 plus 2, right? Or in this case, absolute value of 6 plus the absolute value of negative 2. So 6 plus 2 is 8. So look at the difference. Your total area is 8, but your net area, when you add and subtract the 2, you get 4. Okay, so those are just some examples. Again, we will not be doing negative area for this lesson, but in the next one, when we're in our next chapter, we'll do net versus total. Okay. Here's another example of that happening where C is either positive or negative. If you have a constant, what's really cool for a constant, because it's only a special rule for the constant and the constant only, because a constant helps you make a rectangle. If you go from here to here and you have a constant function, well, it's just going to be that constant, because if that's 6, it's 6 high times 3 and 3 to 14. Well, you're just going to do 14 minus 3 times 6, and you're done to find out that area there, because it's 6 high, and then it's 11 wide, right? So you're going to do 14 minus 3 to get the 11, and then you'll get 66 total units. Don't use this. It's not necessary. Just graph each one of them out, and you will get what you're supposed to, okay? So here's a bunch of examples. I'm pretty much done with the lesson because you're going to just do geometry from here on out, okay? You have to do these exercises here, 7 to 12, and then 13 to 20 for homework. Just take a picture or scan it using Adobe PDF scanner, the Adobe, what do we call it? Let me check my phone. Adobe Scan. Yep, Adobe Scan on your phone. Share the link or share the PDF on Google Classroom. And then you also have this quiz to review. This quiz review, I made this. Oh, sorry about that. I made this on GoFormative. And here's the reason why. You can, by all means, submit this as a PDF. However, I want you to, so that we don't run into issues taking the quiz online, I want you to do it on GoFormative. Okay, I will answer any questions you have on it, but it's really cool. I incorporated Desmos on there, and I want you to like type it into Desmos. And so let's do a practice problem or two from here. Okay, so the first one, and then I'll talk about the review. So the first one, let's graph 5. Let's graph y equals 5. So we have y equals 5, and we have y equals 0, and I have x equals 1 and x equals -2. Okay, so it's going to be between -2 and 1, 2, 3, 4, -2 and 5. Okay, and between -2 and 5. Let me just label everything. So that's between -2 and 5. And then it's going to be between y equals 0 and y equals 5. I am so sorry. I'm mixing up my x's and y's. -2 to 1. Whoops. -2 to 1. Well, lucky I have this iPad. That's easy to fix. Okay, and between 0 and 5. So I got my numbers right at the top. I'm just not paying attention. 0 and 2, 4, 5. So y equals 5, y equals 0. And what you see here is what you are trying to determine. So you're trying to find this area right here in this perfect rectangle. Okay? And so here we have a width of 3, and we have a width of 5. So 3 times 5 is 15. So my apologies, you really don't want to write this information here because the easiest part of this now is going like this equals 15. So you might as well write 15 units squared. Okay? So for all of these, you can graph them and then write equals, and then there you go. Okay? Now, for the negatives, just do below the x-axis and count by, I don't know, maybe, why don't you do -10 there and -20? There you go. So you're going to just figure out your axes however you need to. For -160, you could even just label it like -160, boom, and then you get your line that you got to work with there. Okay? Doesn't matter. You just space it out how you would like to. Just make sure you're labeling the x-axis appropriately where you can fit 0 to 3, and then label your y whatever you need to label it. Okay? Let's do a little bit more complicated one. For pi over 2, just call this pi over 2. It is as simple as that. You know what? Let me go down a little bit. There we go. Okay, just call that pi over 2. It's just a number. Like don't go crazy with this. This is y equals pi over 2. So that's like the number 1 point something, right? It's 3.14 divided by 2. So it's half of 3.14, which is about 1.57, 1.56, 1.57. So that number is going to be like that. Just call it pi over 2, and then go from -1 to -4. -4, 1, 2, 3, 4, -4 to -1. Okay. And so it's going to be pi over 2 high by 3 units wide. So it's going to be 3 pi over 2 units squared. Okay. So again, pi over 2 is just how tall it is. And let me change these. I don't really need to color code them. This is x equals -4 and x equals -1, and then it's y equals 0. Okay, so just leave it as pi over 2 high by 3 units wide, and times it together, you get 3 pi over 2 units squared. All right. Square root of 2, these are all constants, even though they might not look like it. So numbers 7, 8, 9, 10, 11, 12 are all constants. Then you get into these, and you're like, Mr. A, how do I do these? Well, take a breath. It's okay. Let's graph this first one. You are going to be between, you're going to do x equals -2, x equals 4. Okay, so let me graph those first. X equals -2 is right here. And we have x equals 4, right? X equals 1, 2, 3, 4. And now we're going to have y equals 0 and y equals x over 2 plus 3. So again, you're always using y equals 0. What I could do, I could call, in theory, I can call the first function x over 2 and the second function the number 3, and I could find in between those two. I just feel like that's more complicated than just calling the first function x over 2 plus 3 and calling the second function y equals 0. Just to me is, you're going to get the same area. It's not going to matter, but it's just more simple to call it those two functions. Okay, so I'm going to graph those two. And I'll move that up. Whoops, this isn't working. Let me try that again. Okay. And now this last one, let me color code this one so it stands out to you. I'm going to color code it. Sure, I'll color code it green. The last one, you can't draw a horizontal line because it's not y equals 5, right? It's a line that has a slope that's more than 0. So let's start at 3. Y equals 3. This is just a line, right? And it has a slope of 1/2, right? Isn't it just y equals 1/2 x plus 3? So I'm going to go up 1 over 2, up 1 over 2, up 1 over 2. In the opposite direction, I'll go down 1 over 2 because that is the opposite of an opposite, which is the same. And now I'm going to graph this, and it looks like that would be the best way to graph it. I'm off a little bit. There we go. That's pretty good. So this one has shading that is right here. So we have all of this area we're trying to find. Isn't that really cool? It's not just a constant, it's not 4 constant functions or equations, I'm sorry. It is something that's changing as we go from left to right. So you have two options here. You can break this into, we can break it into I guess I'll use that shading. You can break it into a rectangle and a triangle. Or my suggestion is to just keep it a trapezoid and do the area of a trapezoid. So I'm going to do something quickly that you can turn your paper. I can't turn my paper here because it's a PDF and I won't be able to change your view. But I'm going to do it, and I'm going to restore it right back to the beginning. So think about your trapezoid this way. Okay, this is base 1. Here's B1 up here, or L1. Let's call it base 1. And base 2. Here's your right angle. Here's your height. So really, the width of it is actually your height, and your heights are actually your bases. Kind of weird, but does that make sense? Because your right angle's happening right here. Okay, that's where your right angle's happening. This base is different than this base, so you're going to be averaging those and then multiplying it by the height. So let me hit back, 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 and I'm going to restore it back to where it was. There we go. So here is base 1, which equals 2. Here's base 2, which equals 2, 4, 5. My height, weirdly, on the base, but remember, direction doesn't matter. You can rotate this, and you see it because you have your right angle right here. Because that's what's going to make your height. The two right angles is what catches the height, okay? And the height is equal to 6. It's 6 wide, okay? So we are going to do the area of a trapezoid is B1 plus B2, base 1 plus base 2 over 2 times the height. Again, putting this in a calculator, you might want to write it like this, okay? Remember, that's how you're going to list it on GoFormative. GoFormative notation. It's going to be the easiest for you. Or you can use 0.5 here. I don't care. That's up to you. Use a decimal if you want or a fraction. But keep this in parentheses and then multiply it by your height. Okay, so area of your trapezoid equals B1 plus B2. So it's 2 plus 5 over 2 times the height of 6. Yep, times height of 6. So it's 7 over 2 times 6, which is going to be, so 6 divided by 2 is 3. 3 times 7 is 21. So the area of the trapezoid, units squared. So this answer is going to be 21 units squared. Awesome. I'm going to do that so that you can see it a little bit better. I will, because that's in grayish, I will move this up a little bit. I will change it, the color, to match. And there you go. So that's good. I hope you can tell it's a 7. And that's how you're going to do these. So they're either going to be circles, they're going to be a trapezoid, maybe 2 trapezoids, especially if you're using the absolute value. Yeah, be careful. Again, this is from 1/2 to 3/2. So it has a width of 2, but you don't know what this is going to look like, okay? I don't want to do all these for you, so I want you to play around and try to graph them. This circle, this is going to be a circle, a semicircle, okay, from -3 to 3. Again, I don't want to graph them all for you. Semicircle. Let me do an absolute value one, though. You know what? I'll do this more difficult absolute value one, okay? So you are, in this case, the absolute value function is opening up downward because it's a negative absolute value of x. So it's going to be opening up downward. So let me just draw that quickly so that you have it. Okay. Let me start. Here you have the absolute value function moving downward. Okay, I'll throw arrows on it. Okay. Now what happened? Well, it looks like it was 1, take that away, right? It was 1, take away the absolute value of x. So if this was a positive absolute value of x, it would have opened up this way. I flip it because it has a negative coefficient in front. It's a -1, okay? So it was really opening downward. Think about it. Absolute value of x, absolute value of 5 is 5 times negative is -5. So it would have been all negative. But as a y-intercept, of 1. And if you don't like the way this looks, how about you just put it this way? Negative absolute value of x plus 1. So you see it has a vertical shift of 1. Okay, so this is a positive vertical shift of 1. So I'm going to move it up 1, just like that. Now I'm also going to graph it between 0, right? So it's between 0. And now it's also be between 1 and negative 1. Okay, so it is x equals negative 1, x equals 1. I don't need to label it again. And let me erase that for now. You know what? No, I'll put it back. I don't want to make it too confusing. Let me just erase that. Okay, so here you have those, and then you have y equals 0. You have y equals 0, and you have y equals negative absolute value of x plus 1. That's where I'll write it. Okay, so I adjust the way it looked. It's almost like negative x plus 1, but in this case, it's negative absolute value of x plus 1. Now, again, you could have thought of this as two equations. You could have thought of it as 1, and then you could have thought of it as negative x. And what happens is, it would have looked more like this. This is really weird, but, whoops. It would have looked like this. I'm sorry. Maybe I shouldn't do this. I don't want to confuse you. What I mean to, yeah, let me not confuse you. Let's leave it exactly the way it is. So 1 minus the absolute value of x, and then that's between that and 0. So here you have this area of a triangle. So the area of a triangle equals 1/2 base times height. So it's going to be equal to 1/2 times your base, which looks like it's 2 units wide, times your height, which is 1 unit high, and that looks like it's half of 2, which is 1. 1 times 1 is 1. So in this case, the area of my triangle is 1. Okay, and that's the shaded region here is right there. All right, so you don't have too many more to finish. Just try your best. This one might have a rectangle and a semicircle because it looks like it's a semicircle shifted up 1 unit. Okay, again, that one might be a rectangle and it might be a rectangle and because I'm looking at it already and I see it's stuck in between negative 1 and 1, but it's shifted up 2. So it looks like if you shift this one up 1, you'll have a rectangle and a triangle, or you can break it into either rectangle and a triangle or 2 trapezoids or whatever. But use your geometry skills. If you need to graph these on a graphing utility, like go onto your graphing calculator, or you can type into Google or Desmos, type them in, and that's fine to do these. Okay, like I said, try to do this on GoFormative because it's just like your quiz. So I already put it together for you to play around with it and better understand it before you take your quiz, because it's going to be a little bit different than anything you've done on the computer, but I think it will be fun. For instance, what you'll do to get the shading, let me just show you the shading for this one. You will do not x equal, so let me write it out. X equals negative 2 and x equals 3. and I'll do y equals 0 and y equals 6. Well, I don't want it to be, I want it to be between all these things. So in you can type these in if you want, okay? You can type these in if you want, but no matter what you have to do, you definitely have to do this one. X is greater than or equal to -2 is what you're going to put into Desmos. And then you're going to put a bracket and you're going to tell it, but I also want X to be lesser than or equal to 3. Okay, so you're telling it look between those two items. And then you're going to say, but wait, hold on. I also want Y to be greater than or equal to 0. But I also want, wait for this, Y to be less than or equal to 6. And what it will do is it will actually graph this rectangle immediately. So again, you don't need these items up here, but you can put them in. You'll see the lines and you'll make sure you're right. But you'll get literally between -2 and 3, 0 and 6, -2, 3, and 0 and 6, you will get this immediate shading on Desmos, which is so cool. It's done for you. Oh, I don't know what is happening. I think I had something held down. Okay, something like that. And then this will be all shaded and it's really cool. It will shade just that for you. Because you can't put all four of them in those restrictions, okay? Those only one of them has to be out of it and the rest have to be in them. Okay? Again, this will also graph the lines for you. So this isn't needed, but I would do it if you have the ability to type in all five. But you definitely need what you see in blue. Okay? All right, this video has been probably an hour by now, so I'll let you go. I just want to make sure you have everything that you need, practice these, and book me with any questions that you have. And that's it for Unit 8, Section 5.2. Good luck.